Addition reactions are a large number of reactions that occur with alkenes and make a variety of products. What they are is when you break that C to C double bond, and it's just making it a single bond and forming two new single bonds to each of those carbon atoms to two different atoms or groups. So it's all converting alkenes to a whole raft of different things. And you're going from where you've got a double bond which can have things added to it, so this is, and we call these unsaturated, to things that are saturated. So it means it can't have anything added to it. And we'll look at these all individually. So we have the first one here, addition of hydrogen, also known as hydrogenation. We do need a catalyst for this to work, a platinum or palladium or nickel. They tend to be metals, and it converts the alkene into an alkane. And so what happens there, you've got the hydrogen there, and you break this bond, form single there, and breaking that bond there, as it converts into the alkane. So again, going from unsaturated to saturated. You can add halogens as well, and you can do it two ways, through X2, X squared, which is, it could be F2 or Cl2 or Br2 or I2, any of those halogens, and you'll end up with a dihaloalkane because you add both. Whereas if you had at HX, you had one hydrogen and one halogen, so you just a single haloalkane. So here we've got the bromine, and the bromine add one to each of the carbons as it breaks that bond, ending up with that dibromomethane, one on each carbon. Whereas if you've got this case here, we've got an H and a, might do this colour, H and Cl. So the H will go to one of the carbons, Cl will go to the other, as you break that double bond to form two new single bonds. So it's just chloroethane. To make dichloroethane, you would add Cl2 instead. Now, if we add this sort of addition of to an asymmetrical alkene, so an asymmetrical molecule, so it's not symmetrical. For example, HX, where it could be HCl or HBr. If you add that to an asymmetrical alkene, you can result in two products. Well, you will result in two products. And one thing you need to be able to determine is which one will get made the most of. That's called the major product. And how we do that is we look to each carbon of the double bond. The one which has more hydrogens in that double bond will gain the hydrogen in the major product. And the other carbon will gain the other group. In the minor product, this hydrogen goes to the carbon with the fewer hydrogens. So here we have HCl being added. So we could add H and Cl this way, or H, same way, Cl to H that way. So I could form hydrogen there, connection in Cl there, or you could add the Cl there and the H there. And you do end up in both situations. But which one forms the most? And if we look at our carbons 1 and 2, because they're the only ones of the double bond, carbon 1 has 2 hydrogens, whereas carbon 2 only has 1. So in the major product, the chlorine goes to position number 2. So 2 chloropropane is the major product, where 1 chloropropane is the minor one. Addition of water results in the formation of an alcohol, and we can do that with catalyzing of of acid. So it's H2O/H plus is often given as its reagent, or dilute H2SO4 in aqueous solution. Again, if the alkene is asymmetrical, you get two products where the rich get richer for the major. And that's because if we look at H2O, it's adding an OH and an H. So if we look again at the same starting material, we can see that carbon 1, because it's got the 2 hydrogens versus the 1 on carbon 2, that gains the hydrogen in the major product. And in the minor product, the carbon with the fewer hydrogens gains the hydrogen there. The final one we can look at is addition polymerization, and that converts an alkene into a polymer, which is a very, very long chain alkane. We often just summarize what's going on by looking at when 3 monomer units, and when we talk about monomers, we're talking about the smaller alkane units, when those react together to make a polymer chain. And you can see how on the sides we've got these just lines there, because they show that it's bigger than what we're showing. We're just showing a small section of it. So you need to be able to go forwards from an alkene through to the polymer, and also identify what the alkene was that made that polymer. So here's an example. The way to do that is to basically write 3 of them out. Can do the double one there. So hydrogen, I usually write them up in 90 degrees, so we're kind of not showing our bond angles anymore, but 3 individual units. Like so, connects them all up with the single bonds, and now we need to delete one of the double bonds because it's an addition polymerization, where I'll actually add those back again because they don't look very nice. We've broken the double bond and added 2 new single bonds, and now the groups that we're adding are other monomer units. So this is the monomer, which is an alkene, and this is the polymer. If you have to name the polymer, all you need to do is add poly in front of whatever the monomer is called. So this one here is 2-methylpropane. So this polymer will be poly 2-methylpropane. Here is a polymer drawn, and now I need to draw what it came from. So I wouldn't draw that, but what came from that? What is the monomer that made that? All you need to do is circle basically at the repeating 2 carbon unit, and there's plenty of them, so I'll circle that one there. Redraw it like so, and then add the double bond, and now that is the monomer that made this polymer. So this is 1 bromo, 1 chloro ethane, ethene, 1 bromo, 1 chloro ethene. So this polymer over here must have been poly 1 bromo, 1